Welcome everybody to part 2 of Newman projections. For this part I'll be discussing the Newman projections, the conformations for butane. So let's get started. So here we have our butane molecule. Typically when we're doing the Newman projections for butane, we look at carbon number 2 and carbon number 3. That will be the backbone. That's what we're going to be directly looking at, carbon number 2 and 3. So what will happen is that we'll see carbon number 2 first, and then we'll see carbon number 3. Okay, so here we have it. Okay, there are 4 conformations for conformers for butane. I'll go through all 4 of them, like I've said, and I'll make a rating scale. Okay, a ranking scale, excuse me, on how one is more stable than the other. Okay, so I'm going to rank it from 1 through 4. 1 being most stable, 4 being least stable, and that should help you guys out as well. Okay, so let's get started. Right here we have our first conformer, and this is called the anti-conformation for butane. Okay, the anti-conformation, clearly as you guys can see, again we're looking down the C2 C3 carbon backbone. We can see that the methyl group attached to carbon number 3. Okay, the methyl group attached to carbon number 3 is 180 degrees apart from the methyl group attached to carbon number 2. Okay, so everything is staggered, and this is the most stable conformation for butane in regards to Newman projections. Okay, it's staggered, 180 degrees apart. We have no eclipsing, anything like that. So let me draw this on the board. Okay, so our first conformation. H. You have both methyl groups 180 degrees apart relative to one another, and everything is staggered. So this is called your anti-conformation. Anti-conformation. Let's put it as anti-conformation. It is staggered. And again, the ranking scale 1 through 4, 1 being most stable, 4 being least stable. So on this little scale that I presented for you guys, the anti-conformation, which is the first conformation that we're talking about, this is considered a 1. This is the most stable. Okay, so now let's move on to, and I'll discuss why it is the most stable compared to the other conformers. So that was our first conformer for butane. Now if we rotate this molecule 60 degrees, okay, as such, okay, now we have moved on to the next conformer, and this, there's not specifically a specific name for this conformer. I came up with my own generic name, and I'll draw it and I'll explain what it is exactly. So this is the next conformer. As you guys can see, everything is eclipsed now, and you have the hydrogen and the methyl group being eclipsed, the hydrogen here and the methyl group being eclipsed, and the 2 hydrogens over here being eclipsed. Okay, so that's our second conformer. Let's draw that right here. Here's a CH3, there's an H here, there's another H there, so it's eclipsing. As you guys can see, so the CH3 is eclipsing with this H is eclipsing with this CH3, and the 2 H's here are eclipsing. I don't have a specific name for it, but I'll call it methyl or CH3 H eclipse conformation. Yeah, pretty generic. Eclipse conformation. Okay, and as you guys can tell, it's eclipsed, and on the little scale that I've presented there, this will be the third most stable, or the second least stable. Okay, so it's number 3. So that's our second conformer. Okay, so this is what we have. Okay, right there, as you guys can see. So now if you rotate this another 60 degrees, as such, we have moved on to our next conformer. Okay, as you guys can see, everything now is staggered. Okay, and however, even though it's staggered, it is not as stable as the anti-conformation. And the reason why it's not as stable as the anti-conformation, okay, both are staggered, but this one, the methyl group, is closer to this other methyl group here. And what that presents to us is a new type of strain, and that is steric strain. And the book definition for steric strain is basically the atomic radii, okay, the radii of a specific atom interacting with the atomic radii of some other atom, okay, in close proximity. So it builds up this type of strain, okay, and steric strain creates greater energy, okay, there's greater potential energy, there's greater strain. So if you had to rate torsional strain versus steric strain in regards to which one causes more more strain, it will be steric strain. Okay, and again, it's because of the atomic radii overlapping or getting in the close proximity to the atomic radii of something else, of another atom. And as you guys can see, this methyl group and this other methyl group, we can't see the atomic radii, but we assume that it is there. Okay, it's invisible, so to speak. And so it's interacting with one another. Okay, so this is the next conformation, okay, for butane, and this is called the Gauss conformation. So let's draw this on the board. So here's your CH3, here's your H, here's your other H, there's your CH3 again, there's your H, H. Clearly this is staggered, right? But the only problem is that now these methyl groups are interacting with each other. They want to get away as far as possible, right? But you're forcing them in a position that they're uncomfortable, and this results in steric strain. This type of strain that is in result to atomic radii basically getting too close to one another or interacting with each other. So this is called the Gauss conformation. Gauss, okay, and this is staggered, and on the scale of 1 through 4, this would be number 2. Excuse me, this is the second most stable. Okay, so let me just rotate this a little bit for you guys. Okay, so there you go, that's our 3 conformers so far. We have one more left. Okay, so this is what we have here. Now if we rotate this another 60 degrees as such, okay, now what we have presented is something that's fully eclipsed. Okay, both methyl groups now are completely interacting with each other. What we have present here is both torsional and steric strain. Again, if you guys remember from the previous part, torsional strain is when you have the bonds, the electrons in each bond that are right on top of each other interacting, and you're forcing them to be in a position that they're very uncomfortable being in. And now you have the steric strain, which is the atomic radii. You have atoms too close to each other. Okay, you're making it very uncomfortable for the atoms also. So now this results in steric and torsional strain, resulting in greater energy, resulting in something even more unstable. Okay, so this is our last conformer for butane, and this is, again, they don't have a really good name for this, so I came up with my own generic name. I would call it either fully eclipsed, or you could call it methyl-methyl eclipse conformation. So let's draw this on the board here. Hopefully I have some room. Here's your CH3, there's your H, there's your H. Okay, let's separate this. Okay. So this is our last conformer, and then you have a methyl group here. Let's draw this right here. You have an H. You have another H. Okay. So there you have it. You have both methyl groups right there eclipsing each other. The H is eclipsing, and the other H is eclipsing. So this results in greater energy, and this is, you can make it simple and call it fully eclipsed. Fully eclipsed. Okay. And clearly it is eclipsed, and on the scale of 1 through 4, this will be number 4. Okay. Fully eclipsed, methyl groups interacting. You have torsional and steric strain. H is interacting, and the other H atoms are interacting. Okay. So there you have it. That is the 4 conformers for butane. I like to draw a little plot for you guys. Okay. I'm going to erase this now. So again, let me just go over this, a little quick review. So the first conformer, let me go with this first. Okay. So the first conformer is this, which is the anti-conformer. Okay. And and the thing is, in this case, we have the angle between this methyl group and this methyl group is at 180 degrees. Clearly this conformation is staggered, very stable, right? The methyl groups are not interacting with each other to cause steric strain. What else? There's no torsional strain, and it's clearly staggered. Now if you rotate this 60 degrees, you get the next conformation, which is again a generic name, which is a CH3H eclipse conformation. You have torsional strain. You have just a lot of eclipsing going on here, and it is the third most stable conformation, or the second least stable conformation. If you rotate this another 60 degrees, you have the gauche conformation. It's staggered, but you have a little bit of steric strain. The methyl groups are interacting with each other. And finally, if you rotate this another 60 degrees, you get the final conformation, which is the fully eclipsed, or you could write methyl-methyl eclipse conformation. You have steric strain, torsional strain over here, and here as well. And there you have it. So let's move on to the plot, the little graph. Okay, so on the bottom, on this x-axis, I'll write, we'll have the 4 conformations. Okay, we'll just put X here. 4 conformers, or 4 conformations. And on the y-axis, we'll have energy. Potential, energy, or just simply energy. Okay? So the first one was anti. Then we moved on to the CH3H eclipsed. Then we moved on to the gauche. Then we moved on to the fully eclipsed. Okay. Another way you guys may have this graph presented to you is in the textbook. They'll have energy versus dihedral angle or something like that, where the angles between the methyl groups are either 60 or 120 or 180 degrees. That's another way of presenting it, which is a little bit confusing. I like to just base the x-axis only on the 4 conformations. So the energy versus 4 conformations graph looks something like this. When in the anti-conformation, we know it's the most stable, so there will be little to no energy involved. Okay, but as you slowly get to eclipsed, you start to build some. There starts to be a lot of strain, right? And you get this type of peak, right, as a result of the energy buildup. Then when you get to gauche, right, we have a little bit of steric strain, but barely any torsional strain because of because the lack of eclipsing, the gauge conformation is staggered. So all we have there is just a little bit of steric strain, no torsional strain. And as we get to finally the fully eclipse, the peak gets even larger because now the methyl groups are interacting with each other, and that is what finally concludes it. Okay, so this is something. It's not exactly, but this is something what the plot looks like, and I'll give you some of the values. Here it is 16 kilojoules per mole. Over here it is 3.8 kilojoules per mole. And finally in the bigger peak we have 19 kilojoules per mole. Okay, and what is the differences between these energies, these levels, is because again we have here it's eclipsing, so we have steric, torsional, strain. In the gauge conformation we're at lesser energy because there is no torsional strain. All we have is just a little bit of steric strain, and then fully eclipse everything. There's a lot of interaction going on. So there you have it. This is the conclusion on Newman projections, and I hope you guys learned something. I hope this answers some of you guys' questions. If not, feel free to leave a comment on the video, and I'll be happy to respond. As you guys have noticed, I respond to questions fairly quickly. Thank you for watching, and I hope you guys have a wonderful day.